Okay. So let's prove this first before stating 2 and 3. So we need to prove that there is a random variable x bar which satisfies those two properties. Okay. So indeed, if you look at this expected value x times indicator A, this is a nice function of A. Okay. So let's consider this as a function of A, which is the integral of x over the set A, right? So we define it for every A in G. So if you remember our discussions on distributions, so that was a motivation for, that was a first step to go to the Radon-Nikodin setting. So indeed, this is the probability measure, or the measure here, and this acts like the density. So this gives a new way to create a measure out of P. So by a lemma in section 2.2 or 2.4, Q is a measure on G. And if you don't remember this lemma, you can even check it yourself. So can also check directly. Because all you need to check is that Q is a measure. So Q of empty set is 0. Well, integral over empty set is always 0. And countable additivity. And for this, you can use one of the results about integration. So if you have a bunch of sets here, you can just add the integrals. So checking countable additivity is also not very difficult. But this measure is not a probability measure. So let me write Q of the full set is what? Expected value of x, right? Q of full set is expected value of x, which can be 0 to plus infinity, because it's a positive random variable. So it's not a probability measure. It can be a finite measure. It can be a sub-probability measure, meaning that some measure with total mass less than 1, or it can have total mass greater than 1. So something between 0 and infinity. Moreover, Q is absolutely continuous with respect to, well, Q is a measure on G, so I cannot directly compare it with P, which is a measure on full F, the full sigma algebra F. So I can only compare this with respect to the restriction of P, with respect to the restriction P of script P on G. So P here is the restriction of P on G. Okay? So Q is absolutely continuous with respect to P, which means what? So if you have a set with P measure 0, then the Q measure of this, which is the integral of that with respect to P under A, well, this is integral with respect under A, so we really integrate on with respect to the smaller sigma algebra. We really use this measure for the smaller sigma algebra. So I can also use the restriction of this. The restriction of this, exactly. Restriction of this over A. So this is going to be just 0. Or you can also say, okay, let me write directly 0. Because probability of A is equal to P of A is 0. insensitivity of integral. Okay? Insensitivity of integral. So the P here, the restriction P, is really the script P itself, but you just look at it on the smaller sigma algebra. So it's not really different. So this is by insensitivity. And the insensitivity of integral. Okay? So this shows the absolute continuity of Q with respect to P. We have it for each A in G. Right? So this proves Q is absolutely continuous with respect to P. So what do you do if you have a measure that is absolutely continuous with respect to another measure? Which theorem do you use? Where did we discuss absolute continuity? Remember, continuous random variables. They are absolutely continuous. Their distribution is absolutely continuous with respect to the Lebesgue measure. And by blah, blah theorem, we have their density, right? Radon-Nikodym theorem, right? So by Radon-Nikodym theorem, a density X bar exists. It is a positive G measurable because our measures are on G, right? Q and P are on G. Positive G measurable random variable such that dq is x bar dp, meaning that q of A can be calculated as x bar of P under A. So dq is x bar dp. And since something that is G measurable is also F measurable, I can also write it as an integral with respect to the full measure P, which is just X bar indicator A. On the other hand, by definition, this is expected value of X indicator A. So projection property holds. Property holds. So the uniqueness of X bar also comes from Radon-Nikodym theorem. Comes from the Radon-Nikodym theorem. So we are done with this proof. So existence of conditional expectations is by Radon-Nikodym theorem. Okay? Existence of a random variable that is G measurable and that satisfies the projection property is thanks to Radon-Nikodym theorem. So here's another use of Radon-Nikodym theorem. And that's why we start from conditional expectations instead of probability A given B, because we want to deal with the conditional expectations of general random variables, general numerical random variables. So just looking at discrete probabilities is not enough for us in this general setting. So we follow this more rigorous approach for conditioning, namely to start with conditional expectations, and then we're going to define next week conditional probabilities distributions in terms of conditional expectations, which is a bit different than the undergraduate courses. Okay? So let's continue with the other statements of the theorem. So part one is the main part. And we're going to state a lot of results just for positive random variables. But as you know, we can always extend things to numerical random variables, namely random variables which can also take negative values. So let x be an integrable random variable. This means expected value of x is a real number. Then the conditional expectation of x plus is finite almost except on a null set in G, and well, let's not assume integrability. X be a random variable whose integral exists, okay? Whose integral exists. Meaning that this is not undefined, this is well defined, and it is in R bar. So now we're going to have OR here. Okay? So for x plus we have this, or for x minus we have this, except on a null set in G. In other words, this is finite almost surely, or this is finite almost surely. So if one of them is finite almost surely, then we can always look at their difference. So define x given G as x plus given G minus x minus given G, and 0 if this thing is not defined. If one of the two terms is finite, which happens almost surely, otherwise let it be 0. So this is the conditional expectation of x given G. This is how we define the conditional expectation of x given G. And we have, so x given G defined this way is G measurable, and it satisfies x given G times V is x times V for every, now bounded, I'm going to say bounded because we deal with signed random variables, bounded G measurable V. Bounded G measurable V. And if x is integrable, then x given G is finite almost surely. Is real valued. Right? So finally, if expected value of x is not well defined, namely the integral does not exist, then we just leave it undefined. Then conditional expectation x given G is left undefined. Well, I realized I forgot to prove number 2. So the only thing that we're going to prove is that this is finite almost surely, this is finite almost surely. So we have expected value of x, which is expected value of x plus minus expected value of x minus. So this is well-defined means either this is finite or this is finite. But if this is finite, since this is a positive random variable, I can write it as the expectation of the conditional expectation. In the first hour, we had this, right? And you can also just take v equals 1 here. Just take v equals 1. Expected value of x is the expected value of its conditional expectation, right? So if this is finite, if you have a positive random variable with finite expectation, then you can say that this random variable is finite almost surely, except on a null set of G. Null set of G because this is, so this random variable is G measurable. G measurable. Okay. And similarly, if you have this following the same steps, you can conclude that this is finite except on a null set of G. So the rest is just following this recipe here. If you have two things that are finite almost surely, their difference is finite almost surely. And whenever this creates a problem, just set it equal to 0, which happens with probability 0. So this part is really not very important. And since you have the same property for x plus and x minus, by linearity, you can also get this property. So there is nothing to prove. There is nothing to prove. And yeah, if x is integrable, this means we have an and here. So the difference will be just finite because these two things are going to be finite at the same time. So this is going to be finite almost surely. And if we have this is equal to infinity and this is equal to infinity, which happens in number 3, we have no way to define a conditional expectation. So we just leave it undefined. So this is the definition of conditional expectation. But yeah, of course, part 1 is the most important part. Namely, to check that some random variable is the conditional expectation of x given g, we need to check that measurability holds and projection property holds. Okay? This tells us how to prove that some random variable is the conditional expectation or is a version of the conditional expectation of x given g. Okay? We're going to look at a bunch of examples now. So let's look at the example, an extension of the example that we discussed in the first hour. So let's say you have A1, A2 in F partitioning omega. Partitioning omega. And you have, okay, with positive probabilities. Okay, so define G as the sigma algebra generated by A1, A2, A3, etc. And also define expected value, conditional expectation x given AI as before, as in the first hour. And finally, define the conditional expectation of x given g as the x given AI times indicator AI. So let's show that this is the case according to the theorem. So heuristically, in the first hour, this was how we define conditional expectation given G. But now we have a theory, we have a theorem telling us the properties of conditional expectation. So let's make sure this heuristic definition satisfies these conditions. Well, that is almost a repetition of what we did in the first hour. So let's check that this is G measurable. So x given g is g measurable since a1, a2, etc. are g measurable, right? By the definition of g, these are all included in g. So it is just constant times indicators of g measurable sets, and then their summation. So let's check the projection property. So let V be a G measurable positive random variable. So again, we have V of the form AI indicator AI for some A1, A2, etc. that are positive. So G is partition generated, right? So A1, A2, etc. So this means our V, if it is G measurable, it must be constant over each of the regions. So let's check projection property. X given G times V. Well, we can look at it in each of the regions 1 to infinity. And in each of those regions, both of our random variables are constant. This is equal to x given AI. This is equal to AI. So we can take them out of the expectation. And now this becomes x indicator AI times AI. And by linearity of integral, or more like the series form of monotone convergence theorem, this is x times AI indicator AI, which is V. So this is x times V, which is the projection property. I did it a bit fast because this is the same as what we did in the first hour for 3 things. But the main reason for discussing it again is to look at the special case. Okay? Let's just take G as no information. Okay? Sigma algebra generated by omega, which is just empty set and omega. So you have only one set in this collection. Just one set. If you have just one set, you have just one value, right? So conditional expectation of x given G is nothing but conditional expectation x given omega, indicator omega. You have one set by this thing over there. Okay, and this is x indicator omega given probability of omega. And this is always 1. So it is just expected value of x. So this is the no information case. No information. If you have no information, your estimate is just the expectation. Okay? So in other words, expectation is conditional expectation under no information. The opposite is the full information case. If you know everything about x, meaning that if you have G equals F, so what is conditional expectation x given F? What is conditional expectation x given f? X is f measurable, and you know f. So what can you say about your estimate? What would your estimate be? You're asked to estimate an f measurable random variable, and you know the information in f. So what does that mean? What does that mean? Given f, what is the estimate of an f measurable random variable x? This is f measurable, right? You don't have to justify your answer. Just guess.
Just x.
Just x, right? Because you know everything. And if you'd like to justify your answer, well, here's what we need to do. We need to check measurability and projection property. So what is measurability? It's f measurability, right? So this is f equals g measurable automatically. And projection property, well, x times v versus, so this is x times v, and here we're going to write x given f times v, but we're just checking that this is indeed equal to this. So the two are, of course, equal, right? X times v is x times v, so there's nothing to prove. There's nothing to check. Okay. So conditional expectations are much like usual expectations. In other words, you can list a whole bunch of results, conditional versions of the results for expectations. But of course, it doesn't mean that proving them is trivial. But we have those results, but I don't want to spend time on proving all of them. So what I'm going to do is just to list those results. Okay? The properties of expectations that are similar to, the properties of conditional expectations similar to usual expectations. Okay, so let's list this as propositions. So let's say properties, okay? Properties similar to expectations. Okay, so let's say x, y, x1, x2, etc. So let these be f measurable random variables. F measurable numerical random variables. So what are the properties of expectations? Expectation of a constant is itself. Now, conditional expectation of a constant is itself. If some random variable is positive, then its expectation is positive. Now its conditional expectation is positive. If you have x greater than y, you also have x given g greater than y given g, because this is also a result that holds for the usual expectations. And so this holds in each of the following cases. For instance, y is positive, expected value of x and expected value of, so this or this is finite, or they both exist. So under similar conditions, we also have linearity. So conditional expectation of ax plus by given g is a times conditional expectation x given g, b times conditional expectation y given g. If we have in each of, again, x, y are positive or x, y are integrable and a, b are reals. Here a, b are positive. And one has to be a little bit careful when reading this statement. So this means what? This random variable is a version of the conditional expectation of ax plus by given g, meaning that this random variable is g measurable and it satisfies projection property, okay? So since conditional expectations are unique, up to almost sure equality, sometimes in books people prefer to write almost surely every time they have an equation about conditional expectations. This is because of the fact that conditional expectations are unique up to almost sure equality. Such x bar is unique up to almost sure equality. Okay? So the same story with densities, if you remember, right? You can change the density on a null set and it is still a density. You can change the conditional expectation on a null set. It is still a conditional expectation. It's another version of the conditional expectation. But in computations, it doesn't really matter which version you use because null sets do not matter in probability theory. Some other properties. Okay. If you have two random variables that are equal almost surely, then their conditional expectations are equal, again, almost surely, in each of the positive case and the case where and or is finite, whatever. And finally, there are limit theorems for conditional expectations. 6 is monotone convergence theorem. I'm going to call it CMON, conditional monotone convergence theorem. Okay, so you have x1, x2 positive increasing. Then the conditional expectation of the limit is the limit of the conditional expectation. Okay, so there is series form of that. So if you have positive random variables, the conditional expectation of the infinite sum is the sum of the conditional expectations. There is Fatu. So if you have, again, positive random variables, the conditional expectation of the lim_inf is less than the lim_inf of the conditional expectations. You can relax this positivity with xn greater than some integrable random variable for every n. And you can also write down reverse Fatu, which I'm going to skip. So there is conditional dominated convergence theorem. Let's say you have some random variable y that dominates all those xn's, so y is integrable. Then you have also the limit exists. Limit xn exists. So the conditional expectation of the limit is the limit of the conditional expectations. And finally, A special case is the bounded convergence theorem, where these things are dominated by some constant, which is always integrable. And again, the limit exists. Then limit of conditional expectation of the limit is limit of conditional expectations. And the proof is a long exercise. Maybe I can assign one or two of them as homework, but not all of them for sure. Okay. So instead of talking about the routine properties that are quite the same as the properties of expectations, I'd like to discuss with you special properties of conditional expectations. Okay? And we already talked about those properties a little bit. Now we're going to state and prove them in full generality. Okay? Let me wait for a second. Okay? So the first special property is so-called conditional determinism, or in a less colloquial way, taking out what is known. Taking out what is known. So remember, when you calculate expectations, you can always take constants out. If you have 5 times x, the expectation of that is 5 times expectation of x. So now, let x be f measurable, and let v be g measurable. Then the conditional expectation of xv given g is v times conditional expectation of x given g. Because v is like a constant with respect to the information stored in g. Think about this. You can take this out just like a constant because you know x. So here you know v because v is g measurable. You can just treat it as a constant and take it out of the conditional expectation. Okay? So this is conditional determinism, or taking out what is known result. Well, all we have to do is to check that this is a version of this conditional expectation. So let's check v times x given g is a version of xv given g. So v is g measurable by construction, by definition. X given g is g measurable by theorem, by the definition of conditional expectation. So their product is g measurable. So there is nothing special going on. Usually, the more interesting part is to check the projection property. Projection property. So for this, we need to pick a g measurable random variable, or let's say the indicator of a g measurable set. We're going to prove that this acts like a substitute of xv. So under this operation. So we're going to show that this is equal to this, hopefully. This is what we need to show, because we try to show that this is a substitute of this under this kind of an operation. Okay. So what is this? This is x given g times v indicator a, right? So expectation of conditional expectation times something that is g measurable. So this is g measurable. And this is conditional expectation with respect to G. Therefore, I can write it as, I can replace this by X, using the fact that this is a conditional expectation. V indicator A. This is what we wanted to prove. Okay. Projection property for X given G. This is all we had to show. So checking that something is a version of the conditional expectation is usually not that difficult, but sometimes it might be like a puzzle. You just need to look at it from the right way, right? You need to recognize or remember that this is a conditional expectation, so we can use a conditional projection property for that, meaning that if I multiply this by something that is G measurable, I can just replace it with X, and vice versa. Okay? Here is one more special property, which is the generalization of the tower property. We're going to call it tower property again, but sometimes it is called time consistency or something else. Okay? So any questions about conditional determinism? That's a very important property of conditional expectation, and it is quite intuitive if you think that this is just no information and this is then a constant. Right? This reduces to the very easy rule about expectations, right? But now it is the conditional version of that, taking out what is known. So tower property or time consistency. The fool beats the genius. Okay, let's see why the fool beats the genius. So let H, G, and F be sigma algebras. So we have H is a subsigma algebra of G, G is a subsigma algebra of F. And let X be positive, F measurable, then so X given H is equal to X given G given H, or X given H given G. The order doesn't matter. Okay. Consider this like a timeline. You have information that is growing, and you have more information over time. Okay? Let's say this is at time 1, this is at time 2, and this is at time 3. You have X that is F measurable. What you do is to estimate it in 2 steps, like this. Or in 1 step, like this. They're equal. They're equal. This is this equality, okay? How about this one? How about this one? Well, what you do is something weird. So you first give it to somebody who knows nothing. So you give it to the fool. So this is the fool, and this is the genius. Well, that's not that genius, right? There is also F. But anyway, let's call it that way. So you give it to the fool, and the fool gives you the estimate. The estimate of the fool is just X given H. What you do is to give this estimate of the fool to the genius again. And the genius can do nothing. There is no way that the genius can improve the estimate of the fool. Estimate of the fool given to the genius equals the estimate of the fool. meaning that the fool wins. At the end of the day, the estimate of the fool is the right one. Okay? So the genius here has no role. Right? Okay, so let's check that. First of all, x given h is h measurable. And since h is a subsigma algebra of G, so it is G measurable by conditional determinism. You can take it out of the expectation under G, conditional expectation under G. So if this is G measurable, you can just take it out. Is 1. Right? So the equality of these two is clear, right, from this. Let's prove the first equality. Let's prove, so this is in 2 steps, let's say. Let's prove that this is a version of this. Okay? Meaning that we need to check that this is H measurable. Well, it is by definition H measurable is already H measurable. And B, we need to check projection property. Well, let V be positive H measurable. So we need to look at this. And hopefully this is equal to, let me write it here. This is equal to the expected value of this times V. This is the random variable whose conditional expectation we are evaluating. So we need to check that these two are equal. And V is H measurable. Well, if V is H measurable, we can put it inside this conditional expectation, again by conditional determinism. Okay. And this is like this times 1, right? So this is also equal to expected value of xv. Expectation of conditional expectation is just expectation by projection property. And if V is H measurable, this is also G measurable. So I can write it as X times V. So they are equal. Well, I could have done the first one in just one shot. Let me do it this way to avoid confusions. V is H measurable, okay? So I can replace this by X. V is H measurable, so it is also G measurable. Therefore, I can replace this by X again. So they are equal. That's the end of the proof for this tower property. Or if you consider these as times, time points, time consistency. Okay, any questions? So these are the two special properties of conditional expectations, which are added on top of the ordinary properties similar to expectations. Tower property and conditional determinism. So next time we're going to define conditional expectations given random variables, and also conditional expectations, no, conditional probabilities. Okay? So have a good weekend.